Let us recall the torsion calculation that we have done last class. We started with a simple calculation of how the distribution of stress due to rotational moment applied to the member fixed at C. First example, we saw for the first example like this, supported at C, how this is behaving for a given rotational moment at two locations on the member. At a n and some distance away from the n, two moments were acting, and we found out the values of stress distribution, right? We found out the values of stress distribution as like this: tau b and tau b and tau a. These two values we found. Okay, these are our answers. Where is the answer? Last answer. This is tau b and tau a was the beginning, I think. Where is tau a? Now lastly we found here, this is tau a. Okay, we found these two values last time at two locations of a and b, I mean 2 points. Okay, okay, we found at two locations, namely point A and point B. By cutting section, we also draw the cross section, how the behavior is, how the distribution is. One is internally, because from the center it is at 20 mm. The other one is to the wall. So we found both of them and plotted. Second question was on shaft with the 3 gears. Okay, the gears are the moments. Gears are the arrangements which applies a rotational moment to the shaft, or in other words, the shaft and gear rotates to produce an energy at the end. It might be running a windmill or a hydropower generation or any type of milling job, right? Having given 3 locations of these moments, last time it was 2 moments, now it's 3 moments acting, and then you are asked to calculate on the member, on the shaft, okay, along the shaft. Last time it was at point, now it is in this case it was given for a shaft AB and BC. We also found out by applying the moments, then we got tau AB and tau BC here. You can see tau AB and tau BC. Okay. Third question was with distributed. Last 2 questions for point moments acting on the, or rotational moments applied at points on the member, but now it's a distributed moments for the member from C until between A and B, point between A and B. In addition to the distributed moments given between C and A, there is another moment given, a point moment at this location equal to 600 Newton meter. We also found out by solving, and you are asked to calculate in this case maximum and minimum. Okay, by maximum you are asked to find maximum and minimum shear stress. We apply the law, the fact that shear stress is 0 at, or shear stress is equal to 0 at the midpoint, or at the center. The distribution of shear stress starts from the center, or otherwise it is away from the disturbances or away from the material. So we found shear stress equal to 0. Oh, sorry, I do the maximum plus, easy for culminating the answer. We found the maximum is at x equals 0, right, or at the center. The distribution starts like this. If it is a circle, the distribution is, we are using circle, it's already there, the diagram is there, I just follow the same thing. So it starts from the 0, it starts from the 0 at the center. One moment. We follow the virtue of distribution of shear stress being 0 at the center, right? 0 at the center to maximum the wall. Along the wall, all through the wall, it will be maximum. Hence, the distance from the center to the wall is important to know how the layers from this point to this point, from center to the wall, is shearing one over another due to rotation. You really have to imagine how this is. Imagine perpendicular to this circle, it is being rotated, being fixed at, and is fixed at C or at the bottom, rotated. So the layer one over another gets twisted or sheared along the, or shear about the longitudinal axis perpendicular to this circle. Okay. We also found these values last time. Moving on, there is another type of question which is number 4. Okay, we are going to solve number 4. Let's do this. You are given with, maybe put the size. Read the question. It is also already given in your tutorial sheet. Let's read the question. This is number 4. My handwriting. Number 4. A shaft is again a circular, because your module has the scope of finding all 4 circle members to understand the twisting moment clearly. Then we go to symmetric square and asymmetric rectangular later on. That will be only theory. I will explain through some nice videos how these members are behaving, especially for building failures. After all, calculations done for circular members. Okay, another member is given, which is a shaft made up of aluminum alloy having an allowable shear stress. Having an allowable shear stress. Let me use the red color. Allowable shear stress. Tau allowable is 100 megapascals. Allowable means what? The working, the design requirement is you need to design to 100 megapascal. The design requirement says, having given the alloy metal and design requirement, shaft diameter also given. Okay, shaft diameter also given 100 mm. Allowable is 100 megapascals. You need to design for. You can take it as a working stress or design stress as allowable stress. The other one is ultimate, or the possibility of the member due to the material of the member. Ultimate strength or laboratory strength, design strength due to the material will be ultimate strength that the material can bear. But coming to the allowable, it stands for the required design or required working stress at the case, for the case. If the diameter of the shaft is 100 mm, determine the maximum torque. So far you are finding shear stress and its distribution. Now it's the problem for finding torque the other way. Same equations can be found, used, but the thing is you need to rearrange and apply the points carefully to resolve, to get the solution for you. Right? Maximum torque that can be transmitted. What would be the maximum torque T if this is the second case? Number 1 question is this one. Number 2, you're asked to find for another case. Last time it was a 60 mm, is it, diameter, 100 mm diameter, right? This is the first case is 100 mm diameter. The second case is 75 mm diameter. Okay, for the second case it is 75 mm diameter. What would be the torque for the 75 mm diameter? Or this says when you reduce the section of the member, what happens to the torque? What happens to the shear stress distribution due to this rotational movement? These are all helpful for designing and troubleshooting your cases at your job site. You are given a designing a column or a member or a beam, right, which is subjected to a lateral loading, tend to rotate. You can play around based on the shear distribution and the failure pattern. You can design accordingly or redesign it. Okay, these are all will come during your planning and analysis of the structure, right? Sketch the shear stress. You should also sketch the shear stress for both cases. When it was 100 mm, and 75 mm. Okay, very simple one. Let's see. You can take it to be, what is this? I repeat once again, there's a different case. What would be the maximum torque if 75 mm diameter hole were bored through the shaft? Hole means what? It's a hollow, right? Indirectly it is saying bored out. It should be bored out. You say bored out. The material is out. Okay, means hollow. This is referring to the material is hollow. Two type of distribution you are going to see. Already you know how the pattern would be. Let's get the magnitude for the given case along the radial line in each case. Okay, so this is the hollow member, diagram A. Let me check, and I use the same notation and the way we are analyzing. I keep the value of the solid one as A. Okay, number one, the figure as A, and this one as B. Easy for us to follow and mark. Okay, very simple solution. The question seems to be longer, but solution is simple. Start writing. Given data, one moment. Okay, you are given with the torsion formula can be applied here, right? It's a solid shaft. Start with the first case of a solid shaft, then we move to the hollow shaft. Very simple answer. Let me write. Given that allowable stress is given, right? Allowable stress meaning the material property is given. Allowable stress is equal to tau allowable. I name this as tau allowable. Allow is equal to, is very thick. Allowable is equal to, but it's better to be thick, right? You can leave it. Tau allowable is equal to, what's the value given to you? 100 megapascals. Okay, 100 megapascals. Keep it aside. And then diameter, solid shaft diameter is given. Diameter of the solid shaft, dia of solid, I put it as solid shaft. Thick shaft or solid shaft is given as. Can you clearly note this point? Solid, solid shaft. Need to write slowly. Solid shaft diameter is given as 100 mm, and then the hollow shaft is given as diameter of the hollow shaft, hollow or the bored out shaft is 75 mm. And then what is given to you? The required answers will be. Let me write the required answers. Required answers are. Bear with me for this. My handwriting is dancing like anything. Required answers. Number one, you asked to find what's the torque. Okay, given the stress allowable, you're asked to find the torque. T, capital T, gentleman T, for the solid and also for the hollow, and also the distribution, isn't it? Two cases, both cases you need to find out the shear stress distribution along a radial line. Okay, you need to find shear stress distribution for the solid, the respective shear stress distribution for the solid, and also for hollow. Okay, let's do one by one. Hollow. Okay, solution. We all know that allowable and maximum stress, allowable and working stress, by relating to allowable and working stress, we are able to find out the required answer. Yeah, you know the moment, right? Our formula, torsional formula, needs the calculation of general calculation. You need to follow the calculate the polar moment. polar moment of inertia. All of you know that. I don't want to repeatedly writing the equation. You know that this torsion and shear are related by polar moment of inertia. Let me find out. Polar moment of inertia, J, denoted by J, which is common for both, right? Material property is common for both, but the value will be differing. For unit value will be same, but the value will be differing due to the packing of the material. This is solid and this is hollow. A bit difference in radius. So let's find the polar moment for the solid first. Will be by formula. Last time I substituted wrongly. Nobody corrected me in the class. It means you're not alert. I'm so sorry. You need to follow up, correct me. Right? Be alert at least to correct me. Right? Whether you are learning, you are becoming champion. Okay, pi r4 by 32 is the formula, correct? I mean 2. Okay, substitute or is 2, still or, then 2. Let's substitute pi times or. How much is or? In this case, first case is 100, right? 50 is the diameter, right? 100 mm diameter. Radius will be divided by 2, 50 mm radius. Okay, I substitute this 50 mm divided by 1000 will be 0.5, right? 0.5, 0.5, 0.5, power 4, correct? Power 4 divided by 4. What is the answer? Get me the answer. And then similarly I write the value for hollow. Let's find out the value for hollow. J hollow will be a differing in, because the diameter, this is a solid member, right? It's a solid member of diameter, radius 50 mm, right? But in the next case, it is, the first case it is a big one. Oh, it's solid. I don't know the drawing tools. Maybe insert circle. I think it is circle. Okay, I got the circle. But it will be running here and there. Getting crazy sometimes. Right, I keep it very nice solid member. So for solid member, a diameter is stay here. Draw. So the diameter is 100 mm, isn't it? 100 mm. Okay. So I substitute the radius this one. In our second case, it's a hollow member. I think I use this to insert a very nice option. I should have the ring. Thank God I have. So hollow ring is also there. I substitute here. Okay. Let's draw a substitute. It's a circle and hollow ring. Diameter, inner diameter, how much is removed? The material of, the question, the material of 75 mm is removed. The rest is 25 only. Okay. The rest is 25 only. Am I right? Is the question correct? 75 mm drawn out, 100 is original, 75 mm hole is made out, the rest will be 25. Come on. So the total is 100, original one, the same one, keep the same size, otherwise you get confused. The same case it was given, material of, a material of 75 mm is removed. Inside 75 mm removed means both sides you deduct, right? Carefully do this value. I put it here. Side calculation here. So okay. 75 mm is removed means 100 totally. 100 minus 75 will be 25. But this 25 is left, right? Only 25 is left. But for both sides, divided by 2, right? Divided by 2. How much is divided by 2? 12.5 on both sides. The thickness will be, right? Am I correct? Are you following? You left it? 25 only. The 25 you need to divide on both sides. Diameter, right? Yeah, diameter. So you left with 25 all through the sides, because n to n, n to n is 100, right? You remove 75, you left with 25, which should be shared by both sides, right? Should be shared by both sides. As I'm doing here, it will be correct. See, sorry, 12.5. Okay. Okay, this is the remaining. So on both sides it will be 12.5. 12.5. Am I right? Is the value correct? Right. Let me mark here 12.5 and 12.5. So accordingly, it's all diameter, correct? I'm doing correct. It's again diameter, but better we write down the or value. We need the or value only, right? We need the or value. I hope you understand this part. Now let me draw gather radius value. Radius, that is also important for this. Maybe I can write right here somewhere. One moment. Okay. We need the radius, right? What is the net radius? Radius will be subtraction between the net radius, right? The radius is we only need this portion. We only need this portion. We only need this portion. The stress is distributed to this size of the member, because it is hollow here, right? There is no such distribution and the material is not there. The material is there for this section only. Just now we found that this is 12.5. Okay, let's find out the distance. Let's find out the distance from the center of these points. Okay, from the center, I'll draw the diagram. From here, we have 1 and 2, right? You know the last one is, this is at 50 mm already. To find out, can you read it clearly? Is it small? Okay, make it bigger. 50 mm. Okay, from n to n is 50 mm. N to n is 50 mm. I left with so touchy. Let me switch off the touchpad. I will do that later. Sometimes I need this. So my material is here, so I need to know what is this distance, the remaining distance, right? Center to this distance. Totally 50, cut 25 will be another 25, right? 50 minus, we already found that this gap is 12.5, isn't it? And this is 50. Can you subtract now? 50 minus 12.5 will be, come on, tell me, how much is it? 37.5. Are you clear with this calculation? Because, okay, I just put order. Okay, this is hollow, right? This is hollow. So I need to find out the net diameter acting at this point, available at this point. We are not a very good artist. That's why nowadays they teach art also in the kindergarten. Nowadays there's no art. It's optional. Okay. 12.5. I now got the net diameter which is to be subtracted. Are you clear with this small calculation? Where we left with 37 point from center to this. Alright. Okay. So I will have this value. This, if I do that one, so I left with this value as 37.5 mm. 37.5 mm. Are you clear? If you have question, you can ask me at the end of the class or immediately. so that and you also cross check my calculations then and there. That is most important. Ayo, I think my space is not enough. Law. Very clear. Let's move. Very simple one. Similar questions will be asked in your exams, tests, and so on. Be careful. Unit is Wherever you have space, please write down. Right below. Oh, my is bad. Okay, let's move on. Pi r power 4. My r is like this. Okay, my r is like this. Pi r power 4. We need to find out the shear stress polar moment of inertia. The main r is 0.05 minus individually r power 4 can r power 4 I have to, or if you want I can write the formula first. This will be capital diameter, outer diameter. I write like this: pi outer minus pi inner, or radius can radius r I put r outer minus r inner. If you subtract, you will get this one. Okay, r outer minus r inner, then you will have this value. That is what we have done here. So r outer minus r inner, we did it. Now we got this value, power 4. I substitute pi. The explanation is over here on the side. Our r will be, capital R will be 0.054 minus 0.0375 kan 375. Maybe I know this bit. Write down pi 0.05 power 4 minus 0.0375 power 4. Stop me if it is not clear at any time. Come on, find out this answer. This will be your tau hollow or T hollow, J hollow, all in meter per 4. All in meter per 4, because I did resolve already into meter, so it will be meter per 4. Get me this answer. We can substitute conveniently in our calculations. Okay, we found the polar moments. Now we are moving on to finding out our required torsion. Recall our torsion formula. We can then find easily. We know that, I write it like this. We know that shear stress is equal to, use the shear stress formula. Use the shear stress formula. We know that shear stress is equal to torque times rho over J, right? Now allowable, I repeat, for the allowable should be equal to allowable. Now you are given with allowable, should be equal to allowable in this case. Okay, what is that value? Better write down 100 megapascals, correct? 100 megapascals. Let me substitute. I need torque, so I separate it out. Torque of the solid, we do one by one. Whether you are asked for two things, right? I make it a solid, torque of solid. I use the same thing, right? Yeah, all solid. Yeah, torque of solid. Solid material will be torque of solid SO is equal to tau allowable, tau allowable. You just rearrange the equation and write down. You can skip doing. Don't wait for me. If you know, you start doing. I request all of you to work along with me, okay, so that you know what is wrong and right. You get good practice of doing things. It's not that you just listen only, okay. You can, because you have enough time while I do editing of this thing. You have plenty of time to write down and follow. Okay, allowable. I just rearrange it in this equation. My T solid will be T allowable. I remove, otherwise you get confused. T allowable, the J will go up. Okay, j will go up, this j will go up, so I end up with row, gentleman row at the bottom. Correct. Row will come down if I rearrange it. Can we now find out the value? Get me the value, please. Let's substitute. T allowable is 100 megapascal. I change it to 10 power 6. Better, huh? You keep it simple units so that uniform. J we already found. You substitute here and then divided by how much is the value of this row. It's for solid, right? The solid diameter will be 100, right? And 50. So distance from the center of the things will be 0.05. Get me the answer for solid tor. That is first answer. And then second answer will be, I give you the answer, then you need to complete. You do some work, otherwise it will become spoon fed. You will not have a practice at all. Okay, kilonewton meter, we got a first answer already. Come on, let's work out for the similar way. We can work out for tau hollow, torque hollow. Okay, so first one we found already, T solid. The same formula I'm using. I use the same formula, and then T hollow will be, repeat the same equation. T hollow will be equal to tau allowable, same for the same allowable stress. J polar moment. This polar moment solid, because it's varying here because of the material. You need to follow the similar respective values, and distance also varying. Let it be here. Substitute. Allowable already there, 100 megapascals, right? 6, 100 megapascals, and then divided by into J already we found out, right? They just substitute the polar moment of inertia here, and the distance is, in this case, is difference. You need to take the difference between these two. Am I right? How much is the value for this one? 0.0375, right? A hollow distance, 0.0375. This one, the diameter. Distance from the center. Can you see my arrow here? Distance, no. The distance from the center to the point of interest or the hollow material, right? It will be 375. So substitute 375. You will get your answer for moment of inertia. You need to substitute here. You end up with T for hollow, and that too in, what is the unit? Torsion. Since I substitute in newtons, it will be Newton meter. Did I write the unit here? Newton meter already. You can change to kilonewton meter later on. You will get it in Newton meter. Change to kilonewton meter. Okay. Get me this answer. With this, the torque value for the two shafts have been found out. Finally, you're asked to find the shear stress. Okay, shear stress distributions, right? Shear stress distribution in the section. Okay, let's draw the shear stress distribution diagram. You follow the same way that we did it. Section A will be, for the section B, it will be looking like this. Okay, I give you time. Can you draw it? I wait for you. Otherwise, I do it. By this time, you should be able to do it. I wait for another 2 minutes.